Humanity did something that should have been impossible. We flew a spacecraft into the atmosphere of a star, and it came back out intact. The spacecraft is NASA's Parker Solar Probe. On December 24, 2024, it screamed past the sun about 3.8 million miles above the surface, moving at roughly 430,000 miles per hour. That's the fastest any human-made object has ever traveled, fast enough to cross the United States in about 20 seconds. And during the closest part of the pass, NASA couldn't talk to it at all. They just had to wait. 2 days later, late on December 26, a single beacon tone came back. Parker had survived. Now, here's the part that should stop you. The place Parker flew through can reach millions of degrees. The spacecraft is built from carbon and foam. So, how does something fly into a star and not instantly vaporize? Before we get to that, let's talk about where it actually went, because it's stranger than you think. Parker did not fly into the visible surface of the sun. It flew through the corona, the sun's outer atmosphere, which extends millions of miles into space. And the corona hides one of the biggest unsolved mysteries in all of physics. Here's the setup. The visible surface of the sun, the part you see, sits at around 10,000 degrees Fahrenheit. That's the heat source. So as you move away from it, things should get cooler, the way they do when you step back from a campfire. But the sun does the opposite. The corona, further out, hits millions of degrees. The atmosphere is hundreds of times hotter than the surface beneath it. It's like walking away from a bonfire and feeling the air get hotter. This is called the coronal heating problem, and it has stumped solar physicists for decades. Something is pumping enormous energy from the lower sun up into the corona, and we still don't fully understand what. So that's where Parker went. Straight into the hottest, weirdest layer of the sun, which brings us back to the obvious question: why didn't it melt? The answer comes down to one distinction that breaks most people's intuition. Temperature and heat are not the same thing. Temperature measures how fast individual particles are moving. Heat measures how much energy those particles actually transfer to something. The corona's particles are moving at insane speeds, so the temperature reads in the millions. But the corona is also almost a vacuum. There are barely any particles out there. So even though each one carries huge energy, there just aren't enough of them to dump that heat into the spacecraft. Think of the difference between sticking your hand in a hot oven versus boiling water at a lower temperature. The water burns you instantly because it's dense and packed with energy-carrying molecules. The thin air doesn't, even though it's hotter. Parker isn't swimming through a million-degree ocean. It's gliding through a million-degree mist so thin it barely touches the ship. Even so, it still needs serious armor. Parker carries a heat shield made of carbon panels around a carbon foam core that's roughly 97% air, with the sun-facing side painted white to reflect away energy. 500 degrees, while the instruments behind it stay close to room temperature. Now, here's a detail almost nobody expects. Getting to the sun is incredibly hard, and not for the reason you'd guess. You'd think falling into the sun would be easy. It's the most massive thing in the solar system, constantly pulling everything toward it. But Earth, and anything launched from it, is already moving sideways around the sun at about 67,000 miles per hour. That sideways speed is what keeps us in orbit instead of falling in. To drop toward the sun, a spacecraft has to cancel out a huge chunk of that motion. It has to slow down, not speed up. So Parker, which launched in 2018, didn't aim at the sun. It aimed at Venus, using repeated flybys to bleed off orbital energy, each pass bending its path tighter and dropping it closer in. It took years of these gravity assists to spiral inward to the record-breaking Christmas Eve pass. Reaching a star turns out to be less about aiming and more about braking. And the mission is named after a man who earned it. Eugene Parker proposed the existence of the solar wind in 1958. The idea that the sun constantly streams charged particles into space. People doubted him at first. Later spacecraft proved him right. NASA named the mission after him while he was alive, the first time it ever named a spacecraft after a living person. He died in 2022 at 94, having lived to see his namesake fly toward the star he spent his life studying. So what has Parker actually found? Even before the record pass, it was rewriting solar physics. It found that the solar wind near the sun is far more turbulent than anyone expected, and it discovered switchbacks, sudden zigzag reversals in the magnetic field carried by the solar wind. The closer Parker got, the more of them it saw. Parker's data suggests switchbacks may be one piece of the magnetic turbulence and reconnection that helps heat the corona and accelerate the solar wind. Not the whole answer to the coronal heating problem, but a real thread to pull. After the December pass, NASA released the closest images ever captured from inside the sun's atmosphere, showing fine structure no spacecraft had resolved this close. And one of the strangest findings was the solar wind U-turn. After a solar eruption, Parker watched material that had been thrown outward fall back toward the sun. Not the whole solar wind reversing, just blobs of erupted material flowing back inward. It revealed that the sun isn't a simple one-way blaster. Its outer atmosphere is dynamic, messy, and self-recycling, reorganizing itself after every eruption. Here's why all of this matters for you. Down here on Earth, the solar wind isn't just a science curiosity. When it hits Earth's magnetic field, the gentle version gives us auroras. The violent version is a problem. The most dangerous events come from coronal mass ejections, gigantic eruptions of magnetized solar plasma. If a big one slams into Earth, it can trigger geomagnetic storms that knock out satellites, scramble GPS, disrupt radio and aviation, and damage power grids across whole regions. The benchmark is the Carrington event of 1859, the most intense solar storm on record, which set telegraph wires on fire. If a storm that size hit our modern satellite-dependent world today, the disruption could be enormous. And this is the real reason Parker flew into the corona. For decades, we've studied solar storms after they launch, like trying to understand a flood by measuring the river miles downstream. Parker measures the solar wind, plasma, and magnetic structures right where they're born. Better data from the source means better models for how eruptions form, which ones turn dangerous, and how much warning we might get. So this wasn't just a stunt or a speed record. For a few hours on Christmas Eve, human engineering flew into the atmosphere of our star, survived a place hotter than anything we could build to withstand on Earth, and sent back measurements from inside the engine that drives space weather across the solar system. We didn't just look at the sun this time. We reached into it. So what's the bigger deal to you? That we finally touched a star, or that the data might one day protect us from it? Drop your answer in the comments and let me know which one hits harder.